Welcome back to The Explainer. I am absolutely thrilled to have you here today because we're going to look under the hood of how we actually protect our digital lives. You know, every single time you buy something online, send a private email, or log into your bank, you're relying on an invisible shield. Today, we are going to explore the anatomy of that secret by diving into the fascinating world of cryptography, and specifically, a revolutionary cipher known as the Data Encryption Standard, or DES. Okay, let's dive into this. Here's our roadmap for today. First, the basics of cryptography. 2, symmetric versus asymmetric encryption. 3, the birth of DES. 4, inside the DES algorithm. 5, keys, shifts, and S-boxes. And finally, decryption and the legacy of DES. All right, starting with Section 1, the basics of cryptography. Before we really get into the machinery, we have to ground ourselves in the fundamental, age-old problem we're trying to solve here. How does a message actually become a secret? Because when you send a string of text over the internet, it's passing through countless routers and servers. Literally anyone listening could potentially read it. So how do we transform that massive public broadcast into a tightly locked vault? Well, the answer is cryptography. By definition, it's a method of protecting information and communications using codes and mathematical algorithms. The whole goal is actually pretty simple. You want to scramble your original message, what we call the plain text, into a completely unreadable format called ciphertext. Only the intended recipient who holds the right mathematical key can turn that ciphertext back into plain text. It's essentially an invisible force field protecting your data privacy, your credit card transactions, the whole shebang. Now, for a modern crypto system to be truly secure, it has to hit 4 key objectives. First up, confidentiality. Just keeping the secret safe from prying eyes. Second, integrity, ensuring the message wasn't altered or tampered with while it was in transit. Third is non-repudiation, meaning the sender absolutely cannot later deny that they sent the message. And fourth, authentication, verifying that both the sender and the receiver are exactly who they claim to be. Hit all 4, and you've got a robust system. Moving right along to Section 2, symmetric versus asymmetric encryption. And this brilliantly illustrates the core difference between the 2 main approaches. In the top flow, notice you have a single blue key. That exact same key is used to lock the plain text into ciphertext and then unlock it back into plain text. But look at the bottom flow. You've got a teal key to encrypt and a completely different green key to decrypt. 2 completely different locks and keys for the exact same pipeline. Conceptually, this is the great divide in the crypto world. Symmetric encryption is kind of like having a shared house key. If you and your friend both have a copy of the exact same secret key, you can lock and unlock messages for each other. It's super fast and efficient. Asymmetric encryption, on the other hand, gives everyone a public key to drop messages into a locked mailbox, but only the owner has the private key to actually open the box and read them. For today's explainer, we are focusing entirely on a legendary symmetric system. Which brings us to Section 3. The birth of DES. Let's start our factory tour simple. DES, developed by IBM in the 1970s, is a block cipher. It takes a 64-bit chunk of plaintext on the left, feeds it into the machine, applies a 56-bit secret key from the bottom, and then spits out a 64-bit block of scrambled ciphertext on the right. It operates on data block by block, 64 bits at a time. But what exactly is happening inside that box? Let's find out in Section 4, inside the DES algorithm. When we crack open the DES algorithm, we see a highly structured, super repetitive process. After an initial shuffle of the bits, the 64-bit data block is passed down through 16 distinct rounds. I want you to think of these rounds as 16 different workstations on a microscopic assembly line. At each station, the data gets mangled using a unique 48-bit subkey that's generated from our original master secret key. Now, what's really interesting about this architecture, which is called a Feistel network, is how the data moves. The 64-bit plaintext is immediately chopped right down the middle into 2 32-bit halves, left 0 and right 0. In each round, the right half passes straight through to become the new left half, but simultaneously, that right half is woven through a complex mathematical function with the round key, and the result is XORed, or basically mathematically combined, with the old left half. They swap places and the cycle repeats. It is just an elegant, mesmerizing dance of data. Section 5. Keys, shifts, and S-boxes. This is where it gets really fun. First, we got to talk about the keys. You might remember a minute ago I said DES takes a 64-bit input but only uses a 56-bit key. So why the difference?
Well, the DES specification actually starts with a 64-bit key, but every 8th bit is just a parity check bit used for error detection. We literally shave off those parity bits and drop them completely, leaving us with a 56-bit master cipher key. But remember, we have 16 rounds of encryption, which means we need 16 different keys. To pull this off, DES splits that 56-bit master key in half and continuously performs a left circular shift for each round. It literally shifts the bits to the left, wraps them around, and then cherry-picks 48 of those bits to serve as the subkey for that specific round. It's a brilliant way to stamp out 16 mathematically related yet uniquely different 48-bit subkeys for our assembly line. Inside the round function itself, right after the data is mixed with the key, we hit the absolute most critical part of DES, the substitution boxes, or S boxes. There are 8 of these little boxes. They take a 48-bit input and physically crush it down into a 32-bit output. They do this by taking chunks of 6 bits and substituting them with 4 bits. This is the only nonlinear element in the entire DES algorithm. It's the chaotic heart of the cipher that makes it so unbelievably difficult to crack just by working the math backward. Let's walk exactly through this matrix logic because, honestly, it is incredibly clever. Imagine you feed a 6-bit chunk into this S-box matrix. Let's say the binary number 101111. The algorithm takes the outer bits, the first one and the last one, which makes the binary number 3. That tells us, okay, look at row 3. Then it takes the 4 inner bits, 0111, which equals 7. That points us to column 7. You cross-reference row 3 and column 7, and boom, you get the output value of 7. That is exactly how 6 bits are magically and securely crushed down into 4 bits.
Okay, let's take a quick breather from the heavy math for a second and look at a really fascinating vulnerability in DES. Because of how the key generation works with those left shifts we talked about, there are 4 specific weak keys. If you accidentally use one of these master keys, the shifting process creates the exact same subkey for multiple rounds. It completely undermines the complexity of the whole cipher. If you're generating keys for DES, you absolutely must program your system to avoid these specific strings of bits.
And that brings us to our final section, Section 6, Decryption and the DES Legacy.
Think about it. We've chopped our data in half, shifted bits around, crushed it through S-boxes, and run it through 16 rounds of absolute chaos. The resulting ciphertext looks like pure random gibberish. So what now? How do we unscramble the egg? How on earth does the receiver get the original message back? So the crucial point is you use the exact same machine. Remember that Feistel network we looked at? Its structural genius guarantees that decryption is just the assembly line run in reverse. You literally put the ciphertext into the exact same algorithm, but you apply the 16 subkeys backward, starting with key 16 and ending with key 1. The left and right halves naturally untangle themselves, perfectly mirroring the encryption process until out pops your original plain text. It's incredibly elegant, right? However, as beautiful as DES is, it is now a piece of computing history. DES is no longer considered secure for modern applications. And, the problem isn't really the algorithm itself, it's the size of the key. A 56-bit lock simply doesn't have enough possible combinations to withstand brute force attacks from modern, high-powered computers. To protect our data today, DES has been replaced by the Advanced Encryption Standard, or AES, which operates on much larger 128-bit blocks and uses massively longer keys, up to 256 bits. Which leaves us with a final, somewhat provocative thought to chew on. DES was an impenetrable fortress back in the 1970s, but today, a standard computer can pick its 56-bit lock with ease. As quantum computing looms on the horizon, how long until tomorrow's machines break the AES shields we all rely on today? The cryptography arms race is constantly evolving, and the math literally never stops. Thank you so much for joining me on this explainer, and keep learning.